Record. Okay. So let's get started. So today we'll be going over the, infinity and plus infinity and minus infinity. So consider real numbers union these two symbols. So no, these two symbols does not belong to R. So a lot of mathematicians call this the extended reals. So okay, so we agree by convention that this inequality is true. So plus infinity for A in R union. And we define, and so beforehand, we only had finite intervals, right? I mean, without introducing this infinity and negative infinity symbol, we didn't have a notion of like these intervals. So, but now we do. So here, this is just, a is less than or equal to x. And x is bigger than or equal to a. So, and then here is the set of x and r such that x is less than or equal to b. So hopefully you know these as just your usual intervals. Okay, so now we could define a notion of a supremum being infinite. So this is definition. So given non-empty set S, we say sup S is plus infinity if this definition. So if S is not bounded above. So you shouldn't think of like, being infinity as like some number. So by definition, like sup S being infinite just means your set is not bounded above. And similarly,
这个就是他说 the course
infimum
taken
of,
in community college does not.
okay, so infimum S is not minus infinity if S is not bounded below, right? Which sort of makes sense, right? Because if you don't have a lower bound, there's some point that keeps going down, right? And similarly, if sup S is plus infinity, there's like always some point in your set which keeps going higher and higher. So we can actually give like a sort of like a mathematical definition for this, right? So S is not bounded above. What does that mean? Well, we could say it's equivalent to saying given for all m bigger than 0, there exists S and S such that S is bigger than m. So hopefully that's clear, right? So not being bounded above means no matter what number m I choose, there's some element in my set that's bigger than it, right? So, and S is not bounded below. Well, it's the same thing, right? No matter what element, no matter what number I choose, there's some element in my set that is smaller than it, right? And in particular, we might as well just choose negative ones. So there exists S and S such that S is less than M. So is everyone clear so far? Okay. So really, when you're asked to prove stuff about supremum, infimum, if nothing is stated about your set, then you have to consider the case where your soup is finite and your soup is infinite, right? But if there's like an assumption that says S is like a bounded set, then you know everything's finite. So, but let me go over a useful thing that we will need. So let's go over like a similar definition for like soup S being like a finite number, right? So soup S is some number M, if and only if for all epsilon bigger than 0, there exists S and S such that S is bigger than M minus epsilon. So let me just, so what does that mean? So here, if the soup is like right here, right? If this is M, right? What it's saying is no matter what number I choose that this has length epsilon, there's always a point S like inside it. So basically it's saying if you take epsilon to 0, it's basically saying you can find a sequence of points in S going to your supremum. Maybe it won't hit your supremum, but there's always a sequence of points that are going to it. So does anyone see why that is the case? So let me ask you this. What if there's some epsilon? So what is the negation of this, right? So hopefully the negation is, hopefully you all know this by now. To negate for all, you just change that there exists. And to negate there exists, you change the for all, right? In S, S is less than or equal to M minus epsilon. So just to remind you why that's true, like if you think of, for all as like everybody, then what's the opposite of like everybody has hair? It's there exists someone without hair, right? So like you can see that the opposite of for all is there exists. And what's the opposite of there is someone like with hair? It's everybody doesn't have hair, right? So yeah, okay. So this is the negation. So what goes wrong if this is the case? If there is some number such that S is smaller than or equal to M minus that number. So if you read that line, M minus epsilon is an upper bound. Yeah? So, but what is sup S? This is the least upper bound. So we have a contradiction, right? If we assume the opposite. So the idea is if not, if I can't find a sequence of points, well, everything must go into it, then it must stop at some point here, right? So if there is some epsilon interval where there's no point S in it, so right here, this part has no point S, then M minus epsilon is my new upper bound, right? And that's a contradiction because sup S is the least one. So like no matter what like epsilon neighborhood you choose, that's close to M, there has to be a point in there that belongs to S, or else you have a new least upper bound. So similarly, infimum of S is M if and only if it's the same thing. So there exists S and S such that S is less than M plus epsilon, right? So here is your lower bound, right? So let me This thing is M, right? No matter what, if I add some epsilon ball, there has to be a point inside, right? Because if there's no point inside, well, M plus epsilon is my new, lower bound. And M plus epsilon, right? M plus epsilon is bigger than M, right? So, and that will contradict the fact that infimum is the biggest lower bound. So, because I found a bigger one. So you see, so basically this is called I guess it's called approximation property of inf and sup, I guess. Okay. So let's go over some, examples. So I think the book, I guess your professor, if he follows the book, goes over like sup of A plus B is sup A plus sup B. So let's do inf. So infimum of A plus infimum of B. So here, again, to show two numbers are equal, you show less than or equal to and bigger than or equal to. So let's show one way. So let's let x be in, is everyone clear what A plus B is? So let me just, so A plus B is the set of A plus B such that A is in A, B is in B. Yeah, so basically if I let x be here, x is equal to A plus B, where A is in A, B is in B, right? But we most certainly know that x is bigger than or equal to what? So the infimum is a lower, like the infimum of A, is that bigger than A or smaller than A? So
Smaller?
yeah, so this is certainly bigger than equal to infimum of A plus B, right? Because infimum of A is smaller than little a. But this is certainly bigger than same thing, right? Infimum of A plus infimum of B, because infimum of B is smaller than little b. So this is true for any x in AB, right? So in particular, it's true for the infimum, right? So here we get one way. So get one way, right? So okay, the other way is a bit harder. So the other way, you will need to use some, epsilon argument, I guess. So let's do that. So let's assume, finite, right? So assume like nothing's infinite for now. So assume like so basically inf is not negative infinity, right? So really quickly, infimum can't be plus infinity, right? Because if infimum is plus infinity, that means your elements are not even in R, right? Because everything must be big, everything in your set must be bigger than plus infinity. So, okay, so assume finite. Now we are going to use the approximation property, right? So I'm going to be using this. So what does this say? It says, so let me just write it here. So approximation property. So I'll use it for infimum of A and infimum of B, right? So for all epsilon 1 bigger than 0. So let me just let epsilon be bigger than 0. So by the approximation property of infimum of A, basically there exists A in A such that A is less than infimum of A plus epsilon 1, right? So again, let me convince you. So, right? So for all my epsilon in the blue box is epsilon 1, there exists, instead of S, it's A and A, right? Such that A is less than M plus epsilon. Well, M here is just, this thing, right? It's just infimum of S. So A is less than infimum of A plus epsilon. And similarly, for all epsilon 2 bigger than 0, there exists B in B such that B is less than infimum of B plus epsilon 2, right? So this is a nice trick. So basically, I want to show that infimum of A plus B is, I want to show the other way, right? I want to show this, right? I need to show that way. So one way to show less than or equal to is, how you're going to do this is, if I'm less than or equal to any, like, basically, if infimum of A plus B is, less than infimum of A plus infimum of B plus epsilon for any epsilon, then we get this, right? So if the way you think of this is, if I am smaller than, so like, if you just think of a single number, like if C is smaller than B plus any number, then C is less than or equal to B, right? Because if C was bigger than B, C wouldn't be smaller, like for sufficiently small epsilon, like this equation wouldn't hold, right? Like for example, yeah. So for example, if let me think. So it wouldn't hold if C was like bigger than B, because if, for example, if like 6 is bigger than 5.9, right? If C was like 6 and B was 5.9, then C would not be less than, 6 would not be less than 5.9 plus, epsilon being, I don't know, 0.01, right? So this would fail. The point is, this has to hold for any epsilon. So that's why I'm letting epsilon be bigger than 0 here, to let epsilon be arbitrary. So okay, so let's continue. So what do I know here from these two inequalities right here? These two. So if I just add it, I get A plus B is less than. So how about this? Let me put it this way. So right here, it holds for all epsilon 1 and for all epsilon 2, right? So I'm going to let epsilon 1 be epsilon over 2. Then the approximation property says there exists A and A such that A is less than infimum of A plus epsilon over 2. And I'm going to let epsilon 2 also be epsilon over 2. So there exists B and B such that B is less than infimum of B plus epsilon over 2. And now let's add it. So I get this, right? Plus epsilon. And this is for all epsilon, right? But in particular, this thing is bigger than what? This thing is bigger than or equal to I would say, infimum of a plus b, right? Because little a plus little b is an element of big A plus big B, right? And infimum is a lower bound. So this is just the definition of being a lower bound. Then you have this, right? So my infimum of a plus b is less than infimum of a plus infimum of b plus any number, because epsilon was arbitrary. So if I'm less than something plus any number, I'm less than or equal. It's going to be less than or equal to, right? So question, why did I assume finite here? So where exactly did I use finite? So does the approximation property make sense if infimum of a was like negative infinity? A is less than negative infinity plus epsilon 1. It doesn't, right? So like you can't really, we never really define what it means to like add infinity or minus subtract infinity, right? So here is when we use finiteness. Now if you go back above, right here, this part, this whole proof here, I never used the fact it was finite, right? So here, the greater than or equal to part, so if infimum of a plus b was negative infinity, we are done, right? Because we have negative infinity is bigger than or equal to something, right? Negative infinity means you're not bounded below. So like it clearly forces, it clearly forces infimum of a plus infimum of b to be negative infinity, in which case they're equal. So the only case we have is if infimum of a or infimum of b is negative infinity, right? So what if so what does this mean? So we have two cases, right? Infimum of a is negative infinity and infimum of b is negative infinity. And without loss of generality, I can just assume this, right? Some number, right? If it was infimum of b that was negative infinity and infimum of a that was some number, then just swap roles, right? So hopefully the top part is simple, right? So the top part, you should get basically, if this is true, then infimum of a plus b has to be negative infinity, right? We want this, then want. So for the top case, since a is not bounded below, b is not bounded below, I'll leave it up to you to show a plus b is not bounded below, right? Hopefully you could do that. So here, the second case is also the same, right? Because if, so I want to show infimum of a plus b equals negative infinity, i.e. infimum of a plus b is not bounded below. So let's go back to what not bounded below means, right? So not bounded below, right here. For all m less than 0, there exists s and s such that s is less than m. So for all m less than 0, there exists x in a plus b. So without loss of generality, I'll write, since it's an a plus b, x equals little a plus little b, and such that x is less than m, right? I need to show this. Well, I know for this part, this is, let me call this 1. So we're doing 2 right now. So I'll leave 1 to you because that should be fairly simple. Okay, well, 2, we can use the approximation property for the infimum of b, right? So let epsilon be bigger than 0, then there exists b and b such that what? M is, so let's go back to approximation property, such that b is less than m plus epsilon, right? So it should be b is less than m plus epsilon. So why is this good? Because we know infimum of a is can get as small as we want, right? Because infimum of a is negative infinity. So infimum of a is negative infinity means for all, I'll use m1 because I used m on top. For all m1 less than 0, there exists y. There's this, yeah, I used really bad letters, but there exists y in a such that y is less than m1, right? So this holds for all m1. So what I am going to do is, what we're going to do is I need to show this for all m, right? So let's let m be less than 0, and let's find some term that's smaller than m, right? So what I'm going to do is I'm going to let m1 be equal to m plus, what do I want a plus b. So y plus b. So I want m minus m minus epsilon. Yeah. So from this, so I'm choosing my m1. So there exists y such that y is less than m1, which is less than m minus epsilon. Now we're done because we have this thing and this thing. So if I add, so y and a, y plus b is less than m plus epsilon plus m minus epsilon, and we are done. So yeah. So the reason I use the approximation property, you could have just chosen any element, but I just wanted to use the approximation property so we're all clear on that. So this element is in A, right? This element is in B. So so y plus b is in a plus b, right? So we are done. So we showed infimum of a plus b is negative infinity. Okay. So the infinite case, you just have to consider it separately, right? Like there's no avoiding it. So let me just do more examples. So let's do something like 5.5 and 5.6. So what I did was 5.7, yeah. The equality involving infimums, because the book did the equality involving supremums. So okay, let's do 5.5. Inf is less than sup s. So infimum s is less than sup s for every non-empty subset S of R. Okay, so really quickly, let's just do the infinite case, right? What if infimum of S is negative infinity? Then S is not bounded below, right? in which case this inequality is always true, right? I don't care what sup is. If I'm not bounded below, I'm less than every number. So we are done, right? So in this case, the infinite case is easy. So if sup of s is infinity, we are also done because I'm bigger than every number. I'm not bounded, then s is not bounded above, right? In which case, I don't care what inf is because I'm already bigger than like any number. So we are done. So in this case, the infinite case is easily, like, you could take care of it really easily. So now it should be simple because this is just definition, right? Infimum of s, so now finite case. Infimum of s by definition is lower bound, right? Actually, you didn't, you don't even need this actually. So is less than or equal to s for all, and certainly the sup is, for all s in s, yeah. So in that case, we are done, right? Because this is just sup being an upper bound, and this is just inf being lower bound. So I guess in this case, we never really defined what it means for infinity to be uh, infinity to be like bigger than or equal to something. I mean, like we define what it is for like yeah. So if you accept this, so the very top, I guess this proof suffices. So this thing's enough. So basically, if you accept that like infinity is bigger than or equal to, if not, you have to use the definition of like bounded below, bounded above. Okay, so let me go. Let's do one more. So let's do 5.6, an even number. So inf t less than or equal to inf s. So s is a subset of t, right? So s t non-empty subsets or sets. Yeah, actually subsets of R. And S is contained in T. And we want to show that inf T is less than inf S. Sup S. So this makes sense, right? Because if I have more elements, if T has more elements, there's a chance I have a smaller element in T that's not in S, right? So my infimum will get, smaller. And the vice versa, right? If T has more elements than S, so it's possible T has an element that's bigger than every element in S. So the supremum of T should be bigger than the supremum of S. So, but let's do this formally. So okay, so really quickly, if infimum of T is negative infinity, 1 is done, right? Because we're smaller than every number. And if sup of T is positive infinity, 3 is done, right? And 2, we proved, right? I mean, I did this like right here. So the infimum is less than or equal to supremum. So we did 2 already. And so we just need to show 1 and 3. And for 1 and 3, we have the, so let's do 3, right? So the sup of S, well, let's let So let me say this. We assumed, so from above, assume sup t is equal to like m, right? Because right here, the infinite case is simple, right? So so let's assume sup t is finite now. Now, by definition, what does that mean? That means m is bigger than or equal to t for all t and t, right? Because sup t is an upper bound. But if it's bigger than every element in t, well, S is a subset of t. So M is certainly bigger than or equal to every element in S, right? If you're bigger than every element in the bigger set, you're bigger than every element in the subset. Let me write this as S is contained in T. Now we're done, right? As M is an upper bound. So by definition, this means M is an upper bound, right? I'm bigger than every element in S, and sup S is least upper bound. Sup S is, right, which is sup T. And then we are done, right? And 1 will be the same thing, right? So for 1, basically we consider let inf t equal m, because again, inf t equals negative infinity. It's obvious, right? So same thing, right? By definition, it's a lower bound. So m is less than or equal to t for all t and t. But if you're less than every element in T, you're less than every element in S, because S is a subset, right? But this means as M is lower bound of S, inf S is greatest lower bound. Inf S is bigger than or equal to M, right? Which is inf T. So we are done. So in general, if they don't tell you that your set's bounded, consider infinite case. Most likely it's obvious, because you have negative infinity is smaller than every number, infinity is like bigger than every number. So assume the infinite case, and then once you're done with that, it's just finite case. And finite case was like last section, right? So
Can
here
you
we just
explain why M is smaller than S?
where
M is smaller or equal to S.
okay, well, you're smaller than every element in T, right? And S is a subset of T. So think of it like this way, right? T is here, S is here. If I'm smaller than every element in T, I'm smaller than every element of a subset, right?
Oh, got it.
Yeah. So okay.
You can just say S is a subset of T and prove that.
Can you speak louder?
Oh, sorry. So is this a formal way to say it? Like S is a subset of T, and
As
then
S is a subset of T. Yeah. I mean, I'm fine with it.
thank you.
Okay. So I'm just gonna briefly go over. I don't think many professors test on this, because nobody thinks of real numbers this way. But there's something called Dedekind cuts, and they are basically of the form A equals sup R in Q of like R less than A. So people view like √2 as a supremum of this set, right? For example. So people view like real numbers as like a supremum of a set. And so like it's a bit weird, right? Because, you know, if I have root 3 is r less than, so like if you view it as sup, right? How do you add? Adding is simple. It's just the set of R1 plus R2 in Q, such that R1, if I call this alpha, oh, this is bad. This thing to be alpha, this thing to be beta, R1 in alpha, R2 in beta, right? And then I, you know, take the sup over that. So a multiplication is a bit harder, but you can see that less than or equal to. What does that mean? That just means that the corresponding sets are subsets. So it just means alpha is a subset of beta, right? Because if you go up like the set of R and Q such that R is less than root 2, that is contained in the set of R and Q such that R is less than root 3. So there's like, so basically like there is a way to construct R, a way to construct R, the real numbers, from Dedekind cuts. You define it as like these sets, and then you add and multiply like that, like this. So I didn't define multiplication because it's harder. There's like some negative issues, but yeah. So for us, we didn't construct R this way. We constructed it by, you know, the completeness. We completed Q, like completeness axiom. So we took, you know, all the values Q approach to. So, but this is like another way. So if you're interested, you can like Wikipedia it. Okay, let me write multiplication a bit harder to define. Due to negatives. Okay, so that's all I have for today. So let me tell you what's on the quiz. So the quiz, the first question, I will actually both questions. First one, prove something with something involving supremum or infimum. Superinf. So this is really what you should study. 2 should be very simple. So the second question is, I give you a set S and find the min of S, sup of S. I don't know why I wrote it in that order, but max of S. Yeah. So 2 should be simple. I give you a set, find these 4 things. So you would just write out what it is.
So when will the quiz be available on the Canvas?
It's on the syllabus, right? So it's your quiz is posted on Thursday.
Oh.
Yeah. So it'll be like this. So I will the assignment will start at 2:00 p.m. Thursday, like California time. And you basically have like 10 hours to do it. Though this quiz should only take like 10 minutes, but
Got it.
yeah. So again, I will upload the questions on the files tab of Canvas. So okay, any questions? So it shouldn't be that hard. I mean the average for like the first quiz was like 90 something. So shouldn't be too hard. Okay. Any questions? Yeah. If epsilon is large, it's obvious, right? Because you want less than epsilon. So if epsilon is large, it's easier to be less than it, right? So we only care for epsilon small. So, okay. Thank you.
Hi, I got a question.
Oh, okay.
So for the question 5.7, you just mentioned so there's an inequality. So for so the inf a plus b is less or equal to inf a plus inf b plus epsilon, and then we can conclude that inf a plus b is less than inf a plus inf b plus epsilon, right? And then we can say like inf a and b is less or equal to inf a plus inf b. I don't know why. Before we just add an epsilon, and then after we get rid of the epsilon, we get the less or equal to. I don't know why.
Okay. How about this? Prove. So basically, I'm saying if alpha is less than beta plus epsilon
Yeah.
for any epsilon, then alpha is less than or equal to beta. Can you show that?
I mean, so what if epsilon is very large? So after we don't have epsilon, then we may have alpha is bigger than beta. Is that possible?
No, but this has to hold for all epsilon. This holds for all.
Oh. So you mean even epsilon is very small, we
Yeah.
still
it'll
get.
hold.
Oh, okay.
That's why
Okay.
my proof. In my proof, I assume nothing about epsilon, right? I just say let epsilon be a number bigger than 0.
Uh-huh.
So is it? I
Okay.
mean, yeah.
Could you
Yeah.
please do a more specific example on this? Do like specific numbers on this?
Like you mean instead of alpha and beta?
Yeah, like 6, like you just did, because I kind of forgot how you did it.
So I mean, I don't know how to. So like, I mean, if you have numbers, you don't need this epsilon argument, right? Because you just look at the two numbers and you know which one's smaller, right? Do you get what I mean?
Yeah.
Yeah, like if I told you what alpha and beta were, you obviously know like which one's smaller, which one's bigger, right? The point was we had like inf, like we didn't know what that number was.
I think my concern is like if alpha is 7 and it's smaller than like 3 plus 10
Mhm.
and epsilon is 10, so
Mhm.
why, so like 7 is not smaller or equal to 3?
Yeah. So again, it has to hold for all epsilon. So this equality has to hold no matter what epsilon I add. In particular, it has to hold when I add, like, say epsilon equals 1, epsilon equals a half, and this doesn't hold, right?
Yeah.
Certainly 3 plus 1. This is not true, right? Yeah, so I'm saying you're missing the for all epsilon. Like, it can't just hold for like one specific number. It has to hold for any number I add. If you get what I mean, like, so I'm basically saying if you just think of alpha and beta as two arbitrary numbers, and I say alpha is less than beta plus any number, any positive number, I guess, then alpha is less than or equal to beta, right? Do you agree with that?
There was a moment I agreed, but I doubted after that.
So if you doubt, like, what numbers are you thinking of?
Just the example I just told you.
So but the example you gave me, this doesn't hold. This doesn't hold. 7 is not less than 3 plus any number, right?
Oh, now I get it. I thought epsilon was like,
A fixed number, right?
yeah.
Yeah, so I'm saying it
Yeah,
should
I
hold
didn't see
for
it
like
as a part of the assumption.
yeah, it should hold for all epsilon
Okay, thank you
greater
so
than
much.
0. Yeah. Okay.
I have a question.
Okay.
For the same problem, you gave us two epsilons, epsilon 1 and epsilon 2. And why you let epsilon 1 and epsilon 2 equals to epsilon over 2?
It's just so when I add it, I get epsilon. It's just to make it look nice. Yeah.
Oh,
I didn't want a 2 epsilon. I wanted like an epsilon. So
okay.
yeah.
So basically for the question 5.7, we just first consider the cases where both the inf of A and the inf of B are not infinity and negative infinity. And then we consider the extreme case, right?
Yeah, pretty much. Infimum cannot be infinity. It can only be negative infinity. You can prove that.
Oh, you mean the infimum cannot be negative infinity?
I'm saying it can't. Infimum cannot be infinity, right? Because what
Oh,
does
yeah.
that mean?
Yes.
It means infinity is a lower bound, right?
Yes, yes.
Yeah, it doesn't make sense.
Yeah, so for the part when you just assume the infimum of A is negative infinity, so you mentioned that for all m, so here the letter m represent the bound, right?
Hold on, let me share. Let me share screen again. So, okay, so you're saying the case where, right here, right?
Yeah, right. The lower bound.
Yeah, I let m be bigger than 0, right? I need to show it for all m less than 0, so I let m be an arbitrary number less than 0.
Okay.
Yeah.
Okay. So the capital M is the lower bound of A, right?
No. M1 is, right?
Oh, so you have M and
This
M1.
thing is an A plus B, right? This
Oh.
thing is an A, right?
Oh, so M1 is the bound of of set A, and M is the bound of A plus B, right?
Yeah.
Okay, okay, makes sense. Thank you.
Okay.